Okay, this is going to be a really short lecture, kind of setting you up to be able to do an independent t-test. So we'll go ahead and get started. This section's all about comparing two means from two samples. This is the heart of what people think of when they think of educational experiments. So here's a couple of examples. In each, the researcher determines a dependent variable of interest, perhaps math scores, drug use, third grade literacy. Then the independent variable is manipulated so that there are two levels or two conditions, such as full versus half-day kindergarten. So look at this one. Our dependent variable is math scores. One level of the IV is kids who eat breakfast, and the other one is kids who don't eat breakfast. Another example, reading scores. And perhaps we've got two levels of the IV. One's a new reading program, and one is the old reading program or some kind of control. Third grade literacy. We could have one group that gets full day kindergarten and one group that gets half day kindergarten, and then how do those affect third grade literacy? We can look at drug use. Kids who go to the DARE program and kids who don't go to a DARE program. Another example, reading fluency. We could compare kids in one zip code with kids in another zip code. In all of these cases, we're going to compare the mean for one sample with the mean for another sample. So what we're really asking is, are the means statistically different? We know that we always risk pulling a sample that is not very probable, way out in the tails of the distribution, just through the luck of the draw. Let's pretend we're comparing the math test means for a group of students who ate breakfast and a group of students who did not eat breakfast. So we pull our sample for the eaters and find a mean of 54%. And then we pull a sample from those who did not eat breakfast, and their mean is only 32%. Looks like we have a difference of 22% between the two means. What we really need to know is how likely we would get a mean of 22 just by pulling a whole bunch of means out of the middle of that underlying distribution. If that 22% difference is really probable, highly likely, just through the luck of the draw of drawing means, then we're going to say that the means are not statistically different. However, if that 22% difference is so unlikely by just drawing different sample means out of the pool from the population, that it's way out in these rejection areas, we're going to say that those means are statistically different. This is a pattern you've seen before. We're going to state a null hypothesis, we're going to set a criterion, we're going to compute the test statistic for the difference in those two means, then we're going to use that test statistic to decide about the null hypothesis and interpret our results. Whenever you run a statistical test, there are some underlying assumptions in the mathematics of that test, and the analysis is valid only if the assumptions that go along with it are met. For the kind of test that we're going to do in this section, there are two assumptions that have to be met. First one is that there are independent samples being used. In other words, one sample can't influence the other. One sample has to be completely unrelated to the other. So for example, if I draw one sample from the group of girls and one sample from the group of boys, they're going to be independent samples, completely unrelated to each other. Another example would be if I pull a group of kids and then I just randomly assign half of them to one group and half to the other group. The two groups don't overlap. They're completely unrelated to each other. The other assumption we have to meet is that there is homogeneity of variance. Remember that variance is measuring the distance between each score and basically the mean for that group of scores. How much do the scores vary around the mean? When we do this test, we're actually going to pool the variance from both groups to estimate the population variance. And so it's going to be really important that the variance be the same in both groups. And that's called homogeneity. If your sample sizes are the same, if the size of one group is the same as the size of the other one, you do not have to worry about homogeneity of variance. Any change in the variance or difference in the variance between the two groups is not going to affect the test. However, if the sample sizes are different, we need to adjust the test if the variance is different in the two groups. This is the null hypothesis for the homogeneity of variance. Basically, we're saying that the variance for one group is the same as the variance for the other group. We want to keep this null hypothesis because it means we can run our test very simply and the variance is the same in both groups. What we do is we take one variance and we divide it by the other variance and we come up with a ratio. If the ratio is really close to 1, we're happy. And we keep this null hypothesis that the variance is the same in both groups. However, if the ratio is very different from 1 and that F statistic that is talked about in your textbook gets high or really small, that means the variances are not the same and we have to run the test differently. I do not expect you to be able to calculate this test by hand, although it's not very difficult and you use a table of a family of F statistics that's a little different than the families of T statistics we've been using. But quite honestly, we simply do this through SPSS a lot more accurately. If the sample sizes are equal, you don't even have to worry about this. You assume that the homogeneity of variance has been met. So now that I've explained the two assumptions that have to be met, I'm just going to kind of insert a note in my steps of testing. After you set your criterion for rejecting your null hypothesis, you have to check that both your assumptions are met and that you're doing the right test.